Understanding physics errors. We're going to talk about errors in this video. Okay, now when we take a measurement, the value we get is very likely not to be the true value. It's almost impossible to avoid errors. What we can do is we can make an effort to minimize errors so that our data is more accurate. Let's define a few terms. The true value is what the value of the quantity actually is that we are measuring. The error is the difference between our measurement, the measured value, or for a set of values, the difference between that and the true value is our error. Accuracy is how close we are to the true value. If we get a reading or a set of reading, like the average of a set of readings, close to the true value, then that is accurate. Then another word, precision. Precision is how reproducible our measurements are. If we take lots of measurements close together, then that is high precision. We are being precise. This is a big source of confusion for many students. The difference between accuracy and precision. If you imagine taking a measurement is like aiming at a bullseye, and the center of the bullseye is the true value. On the first diagram, our readings are very close to the bullseye and very close together. That's accurate and precise. On the second one, we're not very accurate at all, but we are precise. It's a bit like when I play golf. I'm very, very precise, but I'm not very accurate. The third one is actually accurate, because if you took an average of all of those readings, you'd actually end up with something which was pretty close to the middle. So that's accurate but not precise. And the last one is obviously rubbish. It's not accurate and it's not precise. The readings are very far apart, and if you took an average, that wouldn't be anywhere near the center of the bullseye. There are two types of error. There are systematic errors and there are random errors. A systematic error is caused by a fault with the method or the apparatus. It's something's wrong with the system, the way that you actually produced the readings. Characteristically, they will affect every reading. They can usually be identified and you can eliminate them. You can eliminate systematic errors. Random errors, I'll talk about in a bit. They're random fluctuations and they usually can't be avoided. They can be minimized but not avoided. Here are some examples of systematic errors. Something called parallax error. If you read a scale at the wrong angle, you'll end up with a parallax error. A zero error is the result of an instrument which is badly calibrated. If you look at the voltmeter, when there isn't any voltage, there's still a reading there. And that is going to affect every reading. You need to calibrate that voltmeter. And then environmental factors as well can cause systematic errors. For example, if you're measuring the temperature change in an experiment, let's say in a cooling curve, and the temperature, the external temperature changes, and that will affect a lot of readings. Random errors, I said, were random fluctuations. Some of your readings will be too big, some will be too small. So if you take lots of readings and then calculate a mean, then assuming that there isn't also a systematic problem, you should actually end up with a reasonably accurate result. We can quantify the effect of random errors. We can work out something called the standard deviation, but that's not something we have to do on this course. Okay, now while we're here talking about minimizing random errors, is there a better way of measuring the time it takes the ball to fall? And the answer is, of course there is. Perhaps we could do it electronically. Maybe if we used a metal ball dropped by an electromagnet, and then the start and the stop times, basically taking away human error, and the start and stop times could be registered electronically. Maybe we could use a video and we could video the ball falling and then analyze the video afterwards. And another point is if we drop the ball from larger heights, then that would reduce the percentage uncertainty. The bigger something is, then the more accurately we can measure it. Here's a couple of nice diagrams which might help your understanding of errors. On the first diagram, we see our normal distribution of results, of measurements, and the distribution around the mean, this hump shape, that's due to random errors. But then on top of that, we see that there's a systematic error as well, and the systematic error would affect all of the readings. If that wasn't there, then the mean would be the true value if we took enough readings anyway. Also, graphs. I'm going to do another video about graphs, but if you plot a line of best fit, then that's kind of like taking an average, and that is taking into account all the random errors, and then looking at the intercept on the y-axis. That intercept is probably due to a systematic error. That's if the graph is meant to go through the origin.